This is a recording from Reunions Weekend 2009 at the University of Virginia, made possible by the university's Office of Engagement. Many profound questions about the nature of the cosmos are still in their infancy and often fall at the nexus of science, philosophy, and metaphysics. Kelsey Johnson, astronomy professor and adjunct assistant astronomer at the National Radio Astronomy Observatory, explores a number of these issues in this seminar, including the beginning and end of the universe, extraterrestrial life, black holes, dark matter, and dark energy.
Hello, everybody. I am Mary Blair Zacabe. I'm with the university's Office of Engagement, and I want to welcome you to Reunions 2009. We have a great program planned for you today. So now it's my honor to introduce Professor Kelsey Johnson. She's a professor in the astronomy department at the University of Virginia. She also serves as an adjunct assistant astronomer at the National Radio Astronomy Observatory here in town. She's a recipient of the National Science Foundation Career Award and a UVA Fund for Excellence in Science and Technology Distinguished Young Investigator Grant. Those are big titles. She's a recipient of the UVA Excellent and Diversity Fellowship and a winner of the prestigious Hubble, Spitzer, NSF, and Jansky Fellowships. She served on numerous national and international advisory committees. She earned her bachelor's degree in physics from Carleton College and a PhD in astrophysics from the University of Colorado. Please put your hands together and welcome Professor Johnson.
Good afternoon. I am delighted to be here. I hope that you are delighted to be here. I think one of my, well, maybe next to eating chocolate ice cream, but one of my very favorite things to do is talk about astronomy and talk about the universe, and I could do it for hours and hours and hours, and you'll probably have to cut me off. I know you all have things you would like to do later today, but I love talking about astronomy, and I love answering questions about astronomy, so please think of questions as I'm speaking. But for these reasons, I think, in my mind, being a professor, excuse me, is probably the best job in the universe, because I get paid to think about these things and to talk about astronomy. So the first thing I'm curious about is how many of you, while you were students here, had the chance to take an astronomy class? Awesome. One thing you may not know, the astronomy department is very proud of this. You may, it's a little factoid you can tuck away in your head somewhere. The University of Virginia, at the University of Virginia, a higher fraction of our students take an astronomy class than any other institution in the country. Probably even the world, but we don't have the statistics on that. So for whatever amazing reason, this huge fraction of our students take an astronomy class, and it's wonderful to see you come back to learn more. So here we are talking about unsolved mysteries. This is a very pared down 50-minute version. I'll try to make it a 40-minute version so we have time for questions. This is based on a class that I actually started developing here last year at the University of Virginia, and I love teaching it, but it is a tricky thing to teach because we're talking about things we don't know about. And so I get a lot of good-natured ribbing about this from my colleagues, and one of my colleagues asked me the first time I taught it, he said, so, what are you going to have on your final exam? And I hadn't, of course, even remotely started to think about my final at that point. He said, well, I've got a good question for you. Don't solve dark matter. So it is a little bit of a tricky thing to talk about. But my goal in that class, as it is for this seminar, is to really get you to think about how amazing the universe is. And if you don't already think the universe is amazing, I hope you leave this room thinking it's amazing. And if you do already think it's amazing, I still hope you leave the room thinking that it's amazing. And I haven't changed that. But there are just a phenomenal amount of things that we don't know about the universe. Now, we are here in the land of Thomas Jefferson. And so I want to start, there's a rich history of unsolved mysteries that sort of goes back to the beginning of time. The mysteries keep changing, but we keep asking questions. But there's a good one that happened in TJ's day. So, back through recorded history, there have been reports, very strange reports, of these rocks falling from the sky. This is a pretty outrageous idea, right? I mean, rocks are made of rock stuff, and the sky is made of sky stuff, and never the twain shall meet, right? What the heck, it's completely implausible that rocks could fall from the sky. Aristotle even declared that it was impossible that rocks could fall from the heaven. And of course he was right. So this was totally unaccepted. And most of the reports that came in were from these uneducated peasant folk and farmers. They were superstitious. They still did things like sacrifice goats and examine their livers to divine the future, which, by the way, goes by the term hepatoscopy. So if anyone offers to do a hepatoscopy for you, you might decline unless you're fond of examining livers, and I am not. But these reports were all dismissed. But they started getting more credible with time. And now we are in the year 1807, and a very credible report comes from Connecticut, which is really, for practical purposes, just up the road. And so a team of scientists is dispatched to examine the supposed rock that fell from the sky. And the scientists go up there, and they examine the rock, and they look at all of these different lines of evidence to figure out, what is going on with this rock. Could it have really fallen from the sky? Because remember, this is an outrageous idea that rocks could fall from the sky. And they conclude, in fact, that it had fallen from the sky. Well, the news of this report gets to Thomas Jefferson, who is a very scientifically minded man. And this is a quote from TJ when he heard the report. "I would rather believe that 2 Yankee professors would lie than that stones have fallen from heaven." So we have come a long way since 1807. In fact, if you were to pick up an introductory astronomy book, and apparently many of you have, you will note that almost everything in that book we have learned in probably the last 100 years, probably even the last 50 years, if you were to sort of order it by how much we've learned. And I would argue that we are now entering a golden age of astronomy. And this is a little bit ironic if you think about it, because astronomy is the oldest science, and yet it is now only coming into its own. So why is that? It's only now, for the first time, say in the last few decades, that we've really had the technology to look outside of our Earth into the universe. We've opened up new windows. And so the analogy I have in my mind, it's as if you had, I'll say, very awful parents who kept you locked up in a house your entire life without windows. I hope that isn't actually the case for anyone here. And you lived in this house without windows your entire life. Or you had windows, but the window shades were drawn real tight and you can see out. And one day, the window shades opened. You look out one window, and you might see a house. What's that? Huh. Maybe after staring at it long enough, you realize that that house might be kind of like your house. That maybe you live in something that looks like that from the outside. Maybe out the other window, you see a tree. Oh, dear Lord, what kind of exotic object is that? We don't have those in here. You look out the front window, you see a road. What's that? Where does it go? Where did it start? What happens if you go on it? And oh, dear Lord, what if a car drives by? This is totally absurd and unimaginable. And of course, living in this house with no windows most of your life, you wouldn't have these words for tree and house and road and car. You might call them, green stuff and black flat stuff and unidentified moving object. But my point is that is exactly where we are today in astronomy. We've opened up these windows and we see this crazy stuff. We see a house, we can figure out that house is kind of like our house. That's how we are with galaxies and stars. But then we see trees. We don't know what's going on. This is why if you open up an introductory astronomy textbook, you see terms like dark matter, dark energy, black holes. It's all these names that don't actually mean anything because we don't know what they are. So we have come a long way, but we still have quite a bit to do. And I want to start really to help give you a sense of the scales we're dealing with. I mean, the universe is, if you haven't already appreciated this, I hope you will, the universe is unfathomably large. Even for astronomers like myself, we think about these numbers and these scales and these distances on sort of a daily basis. We do the math and we throw the numbers around with huge exponentials here and there, but you don't really internalize what it means. And so I just want to give you a little bit of a glimpse. So if you can see this image here, I don't know if I have a pointer, actually. That's all right. What you see here is the Earth and the moon. Do you see the moon? Shown at their relative sizes and their relative distance. Did you know the moon was that far away? The moon is actually really far away. It's pretty darn impressive that we managed to send people there. Now, granted, we only did it a couple times. We did it 30 years ago, and now we don't have the money to do it again. But we got there, and we came back. That's a freaking long way away. So the other place we send people all the time, of course, is the space station. There are astronauts in residence there now, and there pretty much always are these days. Now, looking at that image, I want you to think, just in your own mind, where would the space station be? Now, space station as a name for the space station is maybe a little bit misleading because of the whole word space. It is a station, and it is orbiting the Earth, but calling it a space station is a little misleading, and here's why. That's where it is. That's not to scale, by the way. The space station barely skims the atmosphere of the Earth. It's 250 miles up in altitude. If you could drive there, you could get there in 5 hours. It's barely in space. I wouldn't even say it's in space. It's sort of in our outer atmosphere. It is not a space station. And that is the farthest away we've routinely been able to put people. And the farthest away we've ever put people is there. The farthest away we've ever sent a spaceship, the Voyager spaceships just left the solar system a couple years ago, and they were launched basically when I was born. That's the farthest we've ever gone. And so learning about the universe is hard. It is very hard, and astronomers are scavengers. And mostly we're scavengers of light. We've learned how to do amazing things with light because that's all we're getting from that stuff out there is the light. But we do what we can. So there's the Earth, there's the moon. Let's zoom out a little bit. Now, I brought my props, and I have really high quality props today. So here, I have a grapefruit. It's fresh. I bought it today from Harris Teeter. The last time I used this, I got a grapefruit, and I had to use it a couple times in a row, and it was rotting by the time I used it the second time, and the gentleman who was holding it was not terribly pleased. But this one is fresh, and I need a volunteer. And what's your name, sir?
Jesse.
Nice to meet you, Jesse. All right, now Jesse is now holding the sun. Make sure you can hold it for everyone to see. It's even roughly the appropriate color. Here's the sun. Now, in your mind's eye, if this is the sun, how big is the Earth? Okay. Now, I'm very fond of the edible solar system. When I do entire edible solar systems with grade school classes, and it works great with kids. They always want to eat Jupiter because Jupiter turns out to be nearly perfectly a peanut M&M. So I have to bring lots of Jupiters when I'm doing this with grade school classes, and I'm sure their parents hate me afterward. So that's the sun. Now I need another volunteer to be the Earth. Are you all ready to see how big the Earth is? It's the only thing edible I could find. And everyone can have one if you'd like. I've got plenty. You can pick which color.
I'll pick a green Earth.
A green Earth. That's nice. I like a green Earth. Well, why don't you just eat them?
All these planets.
All right. That's how big the Earth. Can you hold it up for everyone to see? No. I'm sorry. What's your name, ma'am? Nero. Nice to meet you. Thank you for helping out. Okay. So we've got the sun and we've got the Earth with Jesse and Nero. How far away should you be? Actually, I think if you go to the door, you're probably about right. Now get your head around this. This is the sun. The Earth is the size of a sprinkle, and it's over there. We are so small. Pluto, by the way, would be somewhere by the stadium. Jupiter would be, I don't know, a few times that. Now, this really, in my mind, speaks to human ingenuity because we have taken spacecraft and launched them from this little, green sprinkle that Nero was holding and managed to get all the way out to this tiniest, tiny fleck of dust by the stadium with scientific equipment intact and working and send it back. That's pretty amazing. So the point is, we are so small, and the universe is so large, and if you let it get to you, it can either be incredibly depressing or incredibly empowering. I like to try to edge for the latter, but we'll see. So here's a cartoon image of our galaxy. If anyone ever shows you an image of our galaxy, by the way, it is not actually an image of our galaxy because we've never sent spacecraft outside of our galaxy to take a picture of our galaxy. So this is a cartoon image of our galaxy with our sun shown somewhere out there in suburbia. We're nowhere particularly special. It turns out in the universe it's good to not be anywhere particularly special. Usually the exciting things that happen in the universe are not so good for life. So we're not anywhere particularly special, and that's just fine. So there's our sun. There are billions of stars in our galaxy. I'm sure you've all heard this. You know, Carl Sagan had his wonderful way of saying it. All right, where's that grapefruit? Where'd he go? Just hold it up. All right, there's our sun. Where's the nearest star? Seattle. Seattle. So I don't want to get any ribbing from any of you about why we've not gone to investigate the nearest stellar systems. Seattle. All right, so here's our solar system. Misspoke. Here's our galaxy. I need to be very, very careful because there's this huge misconception. I get students all the time who confuse a solar system and galaxy because they both kind of have the same shape and stuff. This is a lot bigger. So here's our galaxy. There's where we are. We're out in the middle of suburbia. And now I want to show you one more zoom out. And then we'll stop with this size scale exercise. I don't know if the lights can go any dimmer. It might not help. If you ever have the opportunity to see this in a black room, it is absolutely breathtaking. This image is part of what's called the Hubble Ultra Deep Field, taken by the Hubble Space Telescope. And what they did to take this image was they basically took the Hubble Space Telescope and pointed it at this tiny, tiny little spot in the sky for 11 days. Now, to give you some context, a normal, typical observation with the Hubble Space Telescope lasts a couple hours. Observations with the Hubble Space Telescope cost, I mean, we don't pay for it, you do, but they cost on the order of $20,000 or $30,000 an hour, just so you know. They stared at this tiny little spot in space for 11 hours, which is an enormous investment of Hubble Space Telescope time. Sorry, thank you, days. My brain is somewhere over there. 11 days. An enormous, enormous investment of time. So they stared and stared and stared and stared, and almost everything you see in this image is a galaxy. There are a few stars that have sort of managed to find their way in. You can see them because they have these characteristic diffraction spikes, which, by the way, if you haven't had an astronomy class, stars don't actually have. That's just from the optics in the telescope. But you can see a star up there with diffraction spikes. Everything else in here is a galaxy. Some of them are on the order of 12 billion light years away. What that means is that light left these galaxies to get to us 12 billion years ago. We are seeing them as they were at the beginning of the universe. So astronomers have this really nifty tool that I bet paleontologists wish they could get their hands on. We can look back in time. We can look back to almost the beginning of the universe. Now, the word almost there is critically important because it turns out a whole heck of a lot happened in the first, say, 3 minutes of the universe. We can't look back that far. But almost to the beginning of the universe. So everything here is a galaxy. And the universe is enormous. And there's tons of stuff going on. And there are enormous mysteries to be answered. Now, given the enormity of the universe, I hope that you now understand, if you didn't before, how many questions there are. There are so many questions, it's almost hard to even parse them and know where to start. But there are big, governing, sort of large, big picture questions, if you will. And those are the ones that I just want to touch on today, just to give you a flavor of some of the big things that we don't know. And I'm going to fly through these rather fast. And what I hope will happen is that I will pique your curiosity and you'll ask questions because that's far more fun. I think this is a pretty big question. Is there extraterrestrial life? We don't know. That's why it's the Unsolved Mysteries bit. But there are some things that we do know. We can look at what life as we know it requires. And there's actually an entire field now of scientists called exobiologists who study exactly this. And if I had a chance for a second career, I would love to do that. So they look at what is required for life. Well, the first problem is that you have to define life. Turns out that's not trivial. It's very, very tricky to define life. And in almost any definition you put out for life, you can find exceptions. But let's work with the idea of Earth-like life for the sake of being simple. We can imagine crazy Star Trek crystalline entities and all kinds of bizarre things, but let's not go there yet, because that's beyond what we can deal with scientifically. The first thing that life requires is energy. Have to have a source of energy to do anything, right? Nothing in the universe can happen without energy. So you need energy to metabolize, you need energy to move, you need energy to mate and procreate and eat, and everything that creatures do, you need energy. Even computers need energy, right? And in many ways, if you define life, if you don't define it carefully enough, computers are alive. So we need energy. You can get this in a variety of ways. The sun is our primary source of energy on the surface of the planet. You can also do it with heat. So, thermal, volcanic faults and chemical reactions. Those will all be fine, just as long as you have some energy. The second thing you need are elements. Hydrogen's great. Almost all of the universe is made of hydrogen. We know it and we love it. It's the first element on the periodic table, so even if you didn't memorize all 5 billion elements, you probably got hydrogen and helium down because they stick up there like little horns. Not so good for life, though. They don't make very good bonds. And if you want to make complex organisms, you have to make complex molecules. And if you want to make complex molecules, you have to have elements that can do this, and that can do it with strength. The best element to do this with is carbon. All life that we know of is carbon-based, and that's what we mean by carbon-based. That the very essence of what these creatures are made of is fundamentally based on bonds made with carbon. Now, it's possible, second to carbon is silicon. It's possible you could make silicon-based life forms. So science fiction novels about extraterrestrials sometimes latch onto silicon-based life forms, and it might be able to work. We've never seen it, but it might. But we need elements to make complex bonds, to make complex creatures. We need liquid, maybe water. We need liquid to have chemical reactions. We need liquid to transport waste and metabolize. We think the best liquid is water, but we're a little chauvinistic there. We like water. It's not just because we drink water. We really think that water is good for helping to carry out these processes. Methane, liquid methane, could work. We haven't observed it too, but it might. We're trying to be open-minded because, you know what, the universe has some pretty crazy stuff in it. The next thing we need, we think, is an atmosphere. If you don't have an atmosphere, you know what? You're not very protected. Any liquids you have get vaporized. All kinds of nasty stuff happens. So you think we need an atmosphere. We think we need moderate temperatures. If it's too hot, everything gets scorched and burns off. If it's too cold, everything freezes and you don't have any liquid. And you need time. Lots and lots of time. And we need time for evolution to take place to form complex creatures. Now, all of these criteria, and this is only for life as we know it, rule out whole swaths of stellar systems that can't do these things. It could be we're not creative enough or we're not open-minded enough, but if we're looking for life like ourselves, these are requirements that we think exist. So there's some pretty crazy life on our planet, though. This is an example of something called an extremophile. When I taught Unsolved Mysteries this last spring, I actually brought in a demo for extremophiles. It turns out you, too, can go to your local toy store and get extremophiles and raise them. Sea monkeys. are extremophiles, otherwise known as brine shrimp. So I raised brine shrimp for my class, and it worked until the end, and then one day I ran out. Well, I didn't run out of food. Someone stole the food. Now, why would you steal sea monkey food? It was just gone. So I didn't feed them for a month until I got back to the toy store, and then they died. So that was the end of my sea monkeys. But there are things called extremophiles that can live, and not just live, flourish in these unbelievably crazy, harsh conditions. So they can take, extreme cold, extreme heat, extreme dry, vacuums, radiation, all kinds of stuff that would just zap us in an instant. One of my favorite examples is this little bugger up in the corner. This is called a tardigrade. And tardigrades are just amazing. These little buggers, isn't that cute? Don't you want one for a pet? They can withstand temperatures almost down to absolute zero. They can withstand temperatures up to 150 degrees centigrade, so well above boiling. They can withstand vacuum, meaning like vacuum of space. They can withstand complete arid conditions, and they can live without water for 10 years. These things have got a shelf life like you had never seen. Oh, and the other really cool thing they can do is they can withstand 1,000 times the radiation we can. So if we're looking for boogers that can go out and travel in space and not get zapped, these are real good candidates for that. But the point is that, even on our own planet, where we can study the life, there are these crazy, crazy things. And so clearly what happens out in the universe can be even more bizarre. We can actually, because we're scientists, we like to do this, we can actually write an equation to tell you how likely it is that there's life in the universe. This is the equation we use, and you're not going to get tested on this unless maybe you did when you took your astronomy class. This is called the Drake equation. This is Frank Drake here. He's actually, he's still alive and kicking and studying extraterrestrial life, or the possibility thereof at least. This is the Drake equation, and it takes a whole bunch of factors that we think are required for life, and by multiplying them together determines the probability that there is life. Now, there are lots of factors here. Most of them are pretty uncertain. So if you go to your favorite bookstore and you happen to wander through the astronomy section, which I'm prone to do, and then I spend way too much money, you'll find lots of books with titles like Rare Earth or, Life Everywhere. And there are hugely diverging views on the probability of life in the universe based on this equation. And the reason there are hugely diverging views by reputable scientists is because most of the factors in this equation are incredibly uncertain. So it depends on where you want to place your money. Now, some of these we know pretty well. So for example, N stars is the number of suitable stars in our galaxy. We actually have a pretty good idea of that. Likewise, the number of stars, suitable stars that have planets. We have a pretty good idea about that. But then we get down to things here like the survival time, the lifetime survival. That, real uncertain. The question is, how long can a civilization survive once it becomes technologically advanced? And the way we define technologically advanced is capable of sending radio signals. Why do we define it this way? Because if a civilization isn't capable of sending radio signals, we'll never find them, and there's no point in doing this. So what we're interested in is there extraterrestrial life with whom we could communicate? Because if they can't communicate, then we'll never know they're there anyway. Now, survival time. By the definition of being able to send out radio signals, we've been technologically advanced for, less than 100 years. How many times in that 100 years have we come close to wiping out life on the planet? Even if we don't do it, there's a decent chance that a killer asteroid will smack into us some point in the next 1,000,000 years. If that doesn't do it, there's a whole host of other things that will happen, not the least of which being our actual sun dying and scorching Earth. And all kinds of nasty stuff can happen to us. And so how long civilizations survive is critical to whether or not we'll be able to communicate with them. So is there extraterrestrial life is one of the huge looming questions out there. But we are actually making headway in narrowing down some of these parameters. Here's my second question. Completely changing topics. What happens inside black holes? You know, there's this nasty thing about black holes that if you go into them, you can't come out, which makes it kind of hard to do any empirical tests. So I'm showing you this picture here on the right. This is the center of our galaxy. It's known as A star, Sagittarius A star. The center of our galaxy is projected through the constellation Sagittarius. This is the center of our galaxy. It's a super zoomed in image. Oh, see if it'll let me do this. Oh, it's not going to show. Oh, here we go. Come on. It's a time-lapse movie. What you are seeing are stars orbiting nothing. There's nothing there. These are actual observations of stars orbiting the massive black hole at the center of our galaxy. I mean, if you've never seen this before, it's mind-blowing. I mean, you are seeing stars orbiting the black hole at the center of our galaxy. We are now able to do this technologically, which absolutely blows my mind. So what happens in these black holes? Again, the realm of science fiction. All of these unsolved mysteries tend to be great fodder for science fiction, because what better to write fiction about than things we don't know? So lots of crazy things happen in black holes. You know, as many of you probably know, if you go into a black hole, you can't get out. That's why they're black, because light can't get out. But even crazier stuff happens. Now, one of the crazy things that happens as you approach a black hole is, let's say I'm feeling a little bit crazy today, and there's a black hole over there, and I'm going to go check it out. So I'm going to walk over to the black hole. And now I'm walking normally, and then I start walking slower and slower and slower. And I get to what we call the edge of the black hole. It's called the event horizon. And from your perspective, I stop moving. I completely stop. From my perspective, everything's fine. I'm just going on this little trip over here into this black hole. But from your perspective, I have stopped moving. This is general relativity in action. Now, if you've ever had a class in general relativity, you know that it completely messes with your brain. And I like to mess with the brains of my students. So from your perspective, my time has stopped. You know what? If I step over this line and I get into the black hole, from your perspective, my time literally becomes imaginary. The axes of space and time, when you get to the edge of a black hole, get totally messed up. Could be that space becomes time and time becomes space. You know, we can predict some of this mathematically, but it is messed up. When you cross over the event horizon of a black hole, time no longer behaves like time we think of time being. It's very different. Very, very, very different. So that's an example of one of the things that we're pretty sure, we know from models, happens inside of a black hole. Now, one of the problems, aside from not actually being able to go into a black hole and test it, which is clearly a drawback scientifically, is with black holes, we have a real humongous thorn in our side. And that is that, you may have heard this, the laws of physics as we know them break down. They just break down. And let me tell you why. So here's what we've got going on. On one hand, we have Einstein. Einstein was real smart, and he thought up general relativity. And general relativity, generally, it deals with big distances and gravity and mass. But the key here is the big distances and mass. On the other hand, we've got quantum mechanics. Quantum mechanics is this crazy thing about unpredictability. And, you know, we've got Schrodinger's cat. And you know, there's a finite chance that, you know, I'm standing here on this side of the chair, but I could actually be, part of me could be on the other side of that wall. You know, quantum mechanics, like general relativity, messes with your brain. Now, quantum mechanics deals with teeny tiny things. General relativity deals with huge, enormous things. Now, if you go into a black hole, We get into what's called a singularity, super teeny tiny, teenier tiny than teeny tiny could ever be. Realm of quantum mechanics. But on the other hand, it's really massive. It's warping space and time. The very fabric of space and time is being warped, and that's general relativity. And you put general relativity and quantum mechanics together, and they don't get along. You cannot make them work together with our current understanding. And so when we get into this realm where you need both of them, we are totally crippled scientifically because our theories cannot be extrapolated into that realm. So something has to give. And this is a major thorn in the side of physics right now. The current best guess for the resolution to this is something called string theory, and I usually spend a whole week talking about this in my class. If you haven't heard of string theory, I recommend you watch a NOVA special by Brian Greene. He also has a book on it. And it could be that string theory could resolve quantum mechanics and general relativity, but there's this problem with string theory that it's totally untestable. And in science, we don't like things if they're not testable. That's the whole point of science, is for things to be testable. All right, I am rapidly running out of time, and I have, so many more mysteries. So let me just show you what they are to get your juices flowing so you can ask me some questions. Are there other dimensions or other universes? These are things that are very plausible. And in fact, for this string theory to work, we need a whole lot of other dimensions. We think they're what's called compactified. That's really a word we actually use. And they look like this. Do you know that your space looks like this? It's called a Calabi-Yau space. This is a three-dimensional projection of a six-dimensional space. There are good reasons to think there might be other dimensions, and there are good reasons to think there might be other universes. Problem is, currently untestable. Why do we have the laws of physics that we do? Why these laws and not something else? Why do they have the strength that they do? For example, here are the four forces that we know of. We've got gravity up there on the top. That's the one with which most of you are probably the most familiar. We use gravity all the time. It turns out, despite what your intuition might tell you, gravity is lame. Gravity is orders and orders and orders of magnitude lame. Now, I am going to show you what I think is the most impressive demonstration you will ever see. And you too can do this at home with what you have in your kitchen. So here I have an ordinary magnet. It's about the size of a quarter. I have a really good one that has a banana that I like to use, but I forgot it at home. So it's an ordinary magnet. You can take any magnet you have on your fridge, and if anyone here doesn't have a magnet on their fridge, you are way too OCD and you need to get some magnets. Okay, so here's a magnet. And here is, one of these, I don't know what you call these, paper clippy kind of things. You use them all the time. I'm sure they have a name. I don't know what it is. Binder clip, excellent. You all are educated folk. Okay. The entire mass of the Earth is pulling down on the binder clip. And I've got this super stupid little quarter-sized magnet pulling it up. All right, so quarter-sized magnet, entire mass of Earth. Entire mass of Earth loses. Gravity is lame. And physicists don't like this because we don't understand why. Why is gravity so weak compared to all the other forces? We have some theories, but again, we don't know. That's the unsolved mysteries part. So gravity is really lame, and I hope that you keep that experiment in mind and you can go and wow all of your friends over drinks tonight. You can also do the grapefruit thing if you want. So we're made of stuff. Here we've got some wood. I think it's even real. We've got skin and chairs and metal and plastic, which is good. Trees, all of this stuff, air, water, it's all called baryons. It's all called baryonic matter. This is normal matter. But we have to be real careful when we call it normal matter. Why we have to be careful when we call it normal matter? Because we're being awfully short-sighted with that statement, normal. Because it turns out that all of this stuff, the floor, the chairs, the wall, the air, the water, everything that we think of as matter make up less than 5% of the universe. In other words, what I'm telling you is that we don't know what 95% of the universe is made of. Does that bother you? I hope so. So we could explain 5% of the universe, and then there are these two huge other chunks of this pie chart. First, we learned about dark matter. Dark matter is this stuff. We have some hypotheses and theories for it, but we don't know what it is yet. That's why we call it dark matter. Astronomers are real good at making up really bad names for things. So we have dark matter, and we can tell it's there because we can tell it has gravity. We can see things interacting with gravity, but we can't explain what's causing the gravity. It doesn't interact in any other way that we can see with anything else. We've ruled out all kinds of stuff, so you might think, well, have they thought about black holes? Yes, we've thought about black holes. Have they thought about dark things? Well, yes, we've thought about dark. We've ruled out everything normal we can think of, and we're left with a few exotic things. My current money right now, if I were to put money on it, which I won't because I'm far too stingy, is on something called weakly interacting massive particles. These are called WIMPs. These arise out of again, a good name, right? These come out of something called supersymmetric theory. And this might be something a Large Hadron Collider can find. If any of you are following the Large Hadron Collider, let's keep our fingers crossed that it does actually come online. And no, it's not going to make a black hole that will destroy the Earth. So the other thing, the biggest chunk on this pie chart, is dark energy. Now, this is kind of a fun story. So, we're going about our business. The universe is made of stuff. We know it's made of normal stuff. We already know about dark matter. And all this stuff has mass. And so it has a gravitational force associated with it. So if the universe has stuff in it, and all of this stuff has gravity, and gravity pulls things back, the universe ought to be slowing down. By the way, we know the universe is expanding, if you don't know that. The universe is expanding, which is very cool. Space-time itself is expanding. It's not just things flying away from each other. Space itself is expanding. All right, I'll say that again. Space itself is expanding. So space is expanding. We've known this for quite some time, basically since Hubble's day. Hubble was, in fact, one of the pioneers in this. That's why he got a telescope named after him. All you have to do if you want a telescope named after you is find out that the universe is expanding. So space is expanding, but it has stuff in it, and the stuff has gravity. And so things ought to be pulling back on each other. And so even though it's expanding, it should be slowing down. It should be decelerating. And so, this was a super hot topic, and there were these major teams of preeminent astronomers who wanted to find out, well, we know the universe must be decelerating. The question is, how fast is it decelerating? And we want to know this because if we know how fast the universe is decelerating, we can know its fate. Knowing the fate of the universe is kind of cool. We won't be here to see it, but it's kind of cool. You might get a Nobel Prize or something for it. So we have these competing teams of just, super excellent, amazing, well-known astronomers. Now, the key is competing teams here, and they go out to use the super best, most amazing telescopes on the planet. And they get their observations, and they start to analyze them. They think, So they get more observations, and they analyze them. Uh-oh. And they get more observations. They think, oh dear, what's going on? And so they contact the other team. You know what they found? The universe isn't decelerating. It's accelerating. Nobody expected this. In fact, the beauty of this is how the scientific method played out. I mean, we have these two competing teams who went out to find something and found actually the opposite. So the universe is accelerating. And this is mind-blowing. This has ripped open the field of physics to try to figure out what is causing this. We've called it, again, for lack of any sense of naming things, we've called it dark energy. Dark, if you hear the word dark, it really just means we don't know what we're talking about. So we've called it dark energy. And one of the ideas right now, there are some theories, there are a couple different competing theories out there, but one of the ideas is that space itself is sort of embedded with this repulsive energy. It's kind of an anti-gravity, if you will. So the more space you have, the more anti-gravity you have. And the more anti-gravity you have, the more space you have, because it stretches it out. The more space you have, the more anti-gravity you have. And you can see the snowballs. And so we think dark energy might actually be a property of the fabric of space itself. And physically, this makes sense. It's something we call negative pressure. So if I were, I should have brought my high-tech demonstration rubber band here today. If you have a rubber band and you stretch it, it's pressure, right? It's pulling back. That is a negative pressure. And it turns out that a negative pressure acts like negative gravity. And so we think the fabric of space might be behaving in the same way, but we really don't know. That's the unsolved mysteries bit. Okay, so the point is, the take-home message from this question is we don't know what 95% of the universe is made of, and that's kind of alarming. Fate of the universe, probably it won't affect any of us, but it would be kind of interesting to know if our understanding of dark energy is at least roughly ballpark correct. What this means is that space will get bigger, dark energy will get stronger, space will get bigger, dark energy will get stronger, space will get bigger, dark energy will get stronger. Eventually, dark energy will be stronger than any of the other forces in the universe. First, it'll overpower gravity, because gravity's lame. Remember, we've talked about gravity being lame. So it'll rip apart solar systems and galaxies and stuff like that. Then it'll start to overpower the electromagnetic force and the weak force, so atoms and molecules will be ripped apart. Eventually, it'll overpower the strong force, which holds nuclei together, so nuclei will be ripped apart. So basically, we'll just be left with nothing. There'll be sort of, if this understanding of the universe is correct, there could be sort of one electron and one positron within, 15 billion light years of each other, and it'll get worse and worse and worse and worse and worse. And so that is kind of grim. I don't know whether you would prefer a cold, desolate death or a hot, fiery death. I would really prefer neither. Right now, it looks like we're headed towards the cold, desolate death. But you know what? The good news is we don't understand gravity, so maybe we've got it all wrong. How did the universe begin? This is a huge one. I love talking about this in my class, because this is something that often as academics we don't let ourselves talk about, because it opens a whole Pandora's box of issues. But these are issues that I think it's good to talk about, and it's good to talk about the science as we understand it. Now, how did the universe begin from a scientific perspective? Okay, well, we've got the Big Bang. Fine. What caused the Big Bang? Lots of theories there. Could have been a quantum fluctuation. Works out physically. And the deal here is that when a physicist says nothing, it's not the same as a philosopher's nothing. When a physicist says nothing, I've got a vacuum. There's not nothing there. It's permeated with force fields. And that's what a physicist means by nothing. So they get these quantum fluctuations in this field, and it gives rise to a baby universe, and it takes off. And that's all well and good. So that's one explanation. Could have been the birth of a black hole. In fact, there are a number of theories out there that every time a black hole is formed, it creates a baby universe. And everything we see in our universe is consistent with being inside of a black hole. We could be living inside of an enormous black hole. Have you ever thought about that? Could be. And in fact, there are whole theories built up of selection of universe in almost a Darwinistic sense, that universes that are more likely to have black holes are more likely to have baby universes, and so on and so forth. All right, so how did the universe begin? And we end up with causality. And I like the analogy of turtles. And here's a quote from A Brief History of Time. It's sort of an anecdotal story. Let me read it for you. A well-known scientist once gave a public lecture on astronomy. He described how the Earth orbits around the sun, and how the sun in turn orbits around the center of a vast collection of stars called our galaxy. At the end of the lecture, a little old lady at the back of the room got up and said, "What you have told us is rubbish. The world is really a flat plate supported on the back of a giant tortoise." The scientist gave a superior smile before replying, "What is the tortoise standing on?" "You're very clever, young man. Very clever," said the old lady, "but it's turtles all the way down." And this is my way of saying that every mystery leads to another mystery. And is there a bottom super turtle? Do the turtles go all the way down? We don't know. But we love these mysteries, and they're so much fun to think about and talk about, and I hope that, if you get a chance, we can talk about them more later. Thank you.